Very good afternoon, all of you, to hearing these live sessions. Today we'll be answering some of the queries already what you have posted to us. Also, we are looking at the during the live sessions you have the bit relevant query, fluid mechanics queries, which we have covered the topics. Okay, so that's my point is, and this is the third one we are discussing through live YouTube live for this mock course on fluid mechanics. Uh, go ahead. Very basic way I can say it that we we have been discussing about the linear momentum equations and the Bernoulli's equations. And if you look at the derivations of Bernoulli's equations, highlighting this assumptions part, that's what you try to understand more details, okay, to solve any real life problems. So that what is my objective to develop this course. Uh, Try to understand the concept of fluid mechanics through the Reynolds transport theorems, the mass conservations and momentum conservation. And the Bernoulli's equation is nothing but it is a linear momentum equations applied to a stream tube. That's for a steady, incompressible, frictionless. That means where the viscosity dominant is not there, those the regions we can apply the Bernoulli's equations. So if you look at the derivations part of the Bernoulli's equations, the assumptions part, and some of the examples what we have solved it, and few of the exams from the GATE exams. So the basic our idea is that please practice how to use the Bernoulli's equations, how to use the control volume concept, try to look at these pressure diagrams, uh, try to look at the velocity diagrams. Those needs to have a practice, and those needs to find out how to define a control volume, the appropriate control volumes. Otherwise, you need not to do a surface integrals to compute the pressure forces. So those things you try to look at, which is we try to give few of examples, which is quite interesting examples what we have put it. But still, I'll tell you that please go through these books, which are Control Volume, Reynolds Transport Theorem Concept best book like F.M. White, Sinzel Simbala, or the same books. So these the books address the integral concept where they are talking about mass conservations, linear momentums, angular momentums, energy conservations, as well as the Bernoulli's equations, which we derive it unsteady equations as well as the steady equations, incompressibles, and the frictionless. So if you look at that way, I just encouraging you to uh, solve many problems, not to just apply the Bernoulli's equations, but you try to look at whether the Bernoulli's equations is justified for that. That is the reasons, whatever the problems we have solved it, we first sketch the control volume, so sketch the streamlines, then we apply the Bernoulli's equations. So that way you try to develop your concept in the line of Reynolds transport theorems, applications of Reynolds transport theorems for mass conservations, momentum conservations, either angular or the linear momentum conservations, followed by you can look at the Bernoulli's equations. So the basic, again I am to repeat it, please, we tried our level best to bring you, teach the fluid mechanics that levels. We try to give a few numerical examples to solve how to solve fluid mechanics problems of mass conservations, linear momentums or angular momentum uh, in a control volume concept levels. That's what we try to do it, but still I believe it that please do the practicing on that, which will be really help you when you try to solve the real life problems, because then you will not have a confusions that where I should apply the Bernoulli equations. So which I highlighted more, and that's very basic concept. Again, I will tell it why we introduce these partial fluid balls. Whenever you apply this integral concept, this control volume concept, you in generally we don't look at that it's actually fluid flow is happening it. That means there is a streamlines. There are the a flow is going on. It has having the accelerated component. There is a velocity components. There is a pressure difference components are there. So whenever we are solving some academic problems, simplified problems, there we don't look at that how the flow process happens it. For examples, here if I talk about, again I am talking about these the regions where we have a dominancy of viscous effect. Okay, so that's the regions you will have a stagnation stresses will come in. Okay, the stagnation stresses will come it. That's what is P by rho half P square. Okay, see the stagnation stresses part we are talking about, which is has a two components. Okay, one is the pressure component, another the component because of reductions of the velocity at these points. Okay, so that's what is the stagnation stresses. So if you look at that way, you try to understand it, the how the streamlines behaviors happen is. That's the reasons again I want to, those are having a very much interest on the fluid mechanics. There are a lot of flow visualizations tools are available. Flow visualizations. So you can Google it and you can see that flow visualizations thing. And the very interesting flow processes are happens it. Okay. And these undergraduate levels, we are not going to that level. That's what is giving a complicity to the fluid uh, flow processes. So the fluid flow process is, as you know, is a transport process. Everything's happening in the transport, like you talk about heat transport, you talk about mass transport, you talk about fluid flow transport. We also nowadays talk about whole weather systems, the climatic systems we define in terms of the fluid mechanics, mass transport or heat transport mechanism. So you try to understand these, the fluid mechanics is not the knowledge what we gain it. It is not a confined to a knowledge which we talk about only solving some academic problems. If you Google it, is that there is a question is that what is the utility of these Navier-Stokes equations? So you Google it. What the advantage of this? The total computer emanations, the computer games today, whatever we have, we feel very real conditions that the based on the solutions of Navier-Stokes equations. The concept of the data science also depends upon fluid mechanics, the turbulence behaviors. So that's the knowledge you have to build up. So that's my point is that fluid mechanics are very basic courses and a lot of knowledge have been established. Almost 250 years we have a lot of knowledge, we have established it to solve the real life fluid mechanics problems or the transport problems, which is nowadays are used for computer gaming or animations, or you talk about many virtual reality things what you talk about. That's what is possible. So that's what is the basic knowledge of the fluid mechanics, the solutions of very complex problems what we look at. So looking that way, last class there was a questions on the stability of the floating objects, which I define in the classes, but I just have to repeat it. See, if you look at, you have a ship, okay. So any you can see there is a wave generated happens in a oceans, okay. If similar way, there will be a mild wave will be there in case of the river. So because of that, is the ships are stable. If there is a some disturbance, you could do it. If you look at this way, so basically if we are looking at natural equilibrium conditions, okay, where the M coincides with the G, okay. Uh, just have a what is the G? G is the center of gravity and B is the center of buoyancy, okay. You can find a new positions which is called metacenters, okay. So that's again I'll just put it. If you draw a vertical line drawn upward from B intersect a line of symmetry at the point M here is a metacentric height. Now if you look at that, there will be the conditions will come like this, where your M and B, okay, you will have a M is coincidence with a G, okay, that's what is a natural equilibriums will be there. But that's what we don't look at, that M and B will be the same. There is a no rotations will happen it. But in case of these conditions, when BM is greater than PG, just think about there is just a simple pendulum. Okay, so when you give a disturbance, maybe in a clockwise directions, should be a restoring movement should happen in anti-clockwise directions. So that means again it can return back to the same positions. That's what it happens here. So when you have a BM is greater than BG, that means it will have a restoring movement to return the ship to that positions. But if you have a BM is less than PG, you will have a additional overturning moments. So just try to understand the with a line of axis, the metacentric height, the CG, okay, the gravity, center of buoyancy, how this BM relationship with a BG, that's what will show it whether you will have a overturning moment or the restoring moment. That means whenever I'm doing any disturbance because of natural conditions like maybe a cyclonic happening, it's okay. The sea is there in oceans, the cyclones are coming it, okay. So there is the disturbance is happening because of the cyclones, okay. So it's a changing the stability of this ship. In that periods, we can look at that whether we are having this restorative momentums or not, or will have a overturning moment. So this you try to understand it. Here we derive in the class. I am not going to more details. Very simplified cases. Okay, for we derive it how to get the relationship with mg with gv these factors. Okay, I'm again not deriving it. That's what this is a very simple way of derive it. But if you look at any shipbuilding things, they really the buoyancy part and the stability of the ship they consider very interestingly for each cross section. So here, because it's vast fluid mechanics, so I've just confined it to get the relationship with the mg with a gv, how we can get it for a simple tilted floating bodies. Okay, more details you can go any of fluid mechanics is that. Okay, there is a few conditions is that floating instability generally occurs in nature. That's what I'm saying is that if you look at a ship, if it is a floating it, there is a cyclones, so or it have this waves. So sea waves are there. So there is always have the floating instabilities. Okay, you can look it nowadays. The the Antarctic, the sea, the ice, how instability formations are happening. It okay. So that the icebergs are instability formations are happening. That what you can see it. That's what. Uh, so similar way, if you look at that, it is another interesting thing is that fish generally swim in their planes of symmetric particles. The after death, the position is unstable. They float in their flat side body. Okay, that's same concept has come in. Is okay. This is the example I. It's giant icebergs. Okay, you can see in any movies. Okay, and or any National Geographic channels and all, you can see that falling of icebergs, okay, which is becomes unstable, their shape changes, and because of underwater melting, the icebergs overturning is a very rare scene events which is captured by many of the National Geographic channels like traveler channels, they show it. So the basic points what I'm saying that you can see that the plotting of the stability of floating object. Okay, this is my two students who have been helping this course to make more interesting and more uh, uh, points to bring the fluid mechanics into next levels. But we are just encouraging you to look at this international standard of books like FM White, Sinjal Simbala. Okay, that's what is I'm been interacting with you in every week, so that just look at the fluid mechanics, which is a very challenging text. Research problems, challenging problems we have not solved it. Still, we can look at the solutions. That it's necessary to have a very in-depth knowledge of the fluid mechanics, and also your interest, your willingness to visualize the fluid mechanics problems and solve it. So that's the reasons. My point is that that is what our objective, and we try to uh, disseminate it or try to share with our knowledge with you. Okay, there is a very good question is that how do you decide the sign? I think mass was adding is positive and mass leaving is a minus. Okay, I think that's this is the questions I was really interesting questions. But if you try to look it at a control volume level, so I have a control volume. Okay, so simple rectangles. Okay, two dimensional. So if I draw the normal vectors, okay, my normal vector is this. The surface normal vectors, okay. If velocity is coming in these directions, that means it is making a 180-degree with the velocity. That means if I do V dot n product, okay, I'm talking mathematicals, I'll come back to V dot n products. If I look at that, I'll get V cos theta. That means this theta is 180-degree. That means V minus will get it. But in case of the outlet, what it happened? Theta is equal to 0. So you will have a cos theta equal to 1. So that way, when you consider the control volume, you look at the surface integrals v dot n. Okay, what is a components are coming. So that's the reasons we always have this coming in, means this is a traditional thinking that coming in is always a positive, okay, but not that way. Please look at it as a control volume concept. There is a control surface, and the control surface there is a perpendicular, the n vectors is there. What is the angles between this velocity and the n vectors? Is it a 0-degree or 180-degree? If it's 180-degree, you will have a minus component. But the flow is inside to this control volume. If a flow is outside, the mass flux is outside from this control volume, then you will have a positives. So be remember it, because of this, the dot product, the velocity and this normal uh, to the surface, that products, when you do it, we get a positive signs for the outflow, negative sign for the inflow. So please don't look it in your way. When you apply these control volumes, follow these sign conventions of this control volume concept. That's a very good question, and I hope you have understood that part. Okay, so what is the use of fluid mechanics for structural engineers? Okay, I think I've been teaching the students for fluid mechanics first, then coming to structural engineers. Okay, next. If you look at, we have a very interesting problems. Okay, like for example, I'll tell it today when you look at the 100-story buildings, okay, high-rise buildings, okay. Beside the structural engineers, also we look at the acoustic behaviors, what will happen during the wind load, the cyclonic conditions, what will happen due to the earthquakes, what type of interior should be there, the environment conditions will be the inside this, what will the view will get it. All if you look at it is that this all are related to the fluid mechanics. And another things what I want to tell you is that if you look at the continuum hypothesis, there is not much different between the fluid mechanics and structure. Where I'll tell it the structural mechanics is very easy, where we know the relationship between the stress and strain. But in fluid mechanics, we have this stress versus strain rate, not all for the Newtonian fluid. For non-Newtonian fluid, we have a more complexity. The same way, if you talk about, you are looking for a damage analysis, like you have the structures, okay. It also behave like a non-Newtonian fluids. So what my point is that please don't be compartmentalize that thing. I am a structural engineer and the fluid mechanics, what is relevant and all. Okay. But the fluid mechanics the knowledge can always help you to do the structure analysis when you have the structures also as flexible as fluid. So that's my point is that if you look at the fluid mechanics knowledge in the next levels, okay, beyond these Bernoulli equations, there are a lot of applications we can do. The same knowledge way the non-Newtonian fluid concept can be used to analyze a lot of structural problems. So please look at that. So one of the examples what we put it here, many of the times we so often we have been creating a huge infrastructure in coastal belt, okay, Bay of Bengal or Arabian Sea coastal belt. But we are not looking at how much of the what will happen it to the infrastructure like airports, okay, during the super cyclones. Here we have done a very simple calculations, okay, to estimate the wind loads because of super cyclones using the Bernoulli equations and all. But these are the things is a very gross characteristics. But if I want to look at what type of turbulent structures will be created. Okay, if you look at these are the streamlines, there is the wind speed of 250 km per hours, and the roof will be lifted out depending upon the higher pressures what is developed inside these things. But that's one part of the fluid mechanics which we can get it using the standard Bernoulli equations and all. Uh, but if I want to try to look at that within the buildings we have some infrastructure. What is the safety to the human, the passengers, or what is the safety to the people who are there inside that? If you try to do that, because there will be a series of vortex will be there. Okay, what type of interior design we should do it such a way that that can be safe the human persons which are within the buildings. Those level of understanding we should look at. Now the engineers should look at a next levels. Like if there is a cyclones, there is a flow inside the buildings, but whether that flow, the vortex formations are will be the dangerous for the living human being, and what type of interior design we should prepare it. So what I am to telling it that as I've been visited uh, one of the topmost university in uh, Kyoto's disaster prevention research institutes, they are looking in that way. What is a human behavior during this type of cyclonic disasters? Whether we can save them. So, what I'm trying, and that is a necessary. You need to have a fluid mechanics knowledge. That during the super cyclones, what it happens, interior of a buildings. Okay, so those idea, the knowledge has to put it in the next levels. That is what my point is, and you can try to visualize it. Don't look at that concept is one way. Okay. Okay. So when balloon goes up to certain height, means at certain height it recovers equilibrium. Please explain in detail. Abhinandan. Okay. Okay. This question is slightly off from this. But if you know it, if you climb to the Mount Everest, what it happens is actually pressure decreases. Is it correct? So as you go to higher and higher altitudes, this pressure decreases. So because the pressure decreases, your buoyancy force is decreasing it. Does that buoyancy forces making this balloon stable? That's what you think it. With altitudes, the pressure decreases. Or you can look at that another component as the altitudes, as you go higher and higher altitudes, the pressure decreases. Similar way, as I go and higher, the velocity which is more, it also decreases. So you have to try to look at actually what is the reasons when a balloon goes up remains a stable conditions. Is it a reductions of velocity field, or is it a reductions of the pressure field? That's what you try to understand it. Okay, it's a quite interesting questions, but you have to think more it. Okay, again another questions, what will happen to the space? Okay, if you have a capillarity actions in space, h will be the infinity. I think you look at more space technology and all the things which I'm not discussing here anyway. We this course we have designed not for the aerodynamics part or the space part, but these are the questions we can answer it in your uh, personal chattings. Okay, that's what we'll answer it here. Okay. Can you use the fluid mechanics in living plants? I think again very interesting questions. If you look at any living body like ourselves, okay, it's more than 95% we have a water or water like this. So any living bodies, if you talk about there are a lot of water transport is there, the heat transport is there, mass transport is there. So knowledge of the fluid mechanics is a prerequisite to understand any living uh, plants or the animals and all. But now we are not looking the science in that levels. Okay, but things has come now. We have to look it beyond that points. That's what I try to discuss with you. That how these data science, the computer animations, the gaming, haven't taken care of the fluid mechanics. Okay, because you can understand it. Okay, but the fluid mechanics advantage has not taken that much in biomedicals. So but that is the unexplored area is there. But if you look at this computer animations, the gaming, they all have taken the fluid mechanics. But to have a knowledge the fluid mechanics that level for biofluids, that still I think we have not gone to that level, as well as that I can see that the effort on this direction is not that uh, level also. It is both the way things are that the human being never felt the necessity to know about how the blood movements are happening, what it actually happens because of a particular virus infections and all. So that's never it's considered a challenging work, but it's not like that levels because but a lot of studies has been now it's coming up and there are a lot of biofluidics studies are multi-phase biofluids. These are studies are really is coming up, which is quite interesting. Okay, so this questions from Abhishek Jha. In fluid mechanics, it is important to consider interaction fluid with the surrounding. Yes, obviously, because whenever you take any control volumes, okay, it depends upon the surface. Is it that the surface is a fixed? Like for example, so I'll talk about that. Okay, if my fluid mechanics control volume like this, I have a plate here. If I'm moving a plate volume V, definitely it interacts with the structures, the surroundings. If you have another fluid F1 and F2, it all have interactions here between two fluids. You have always interactions. The fluid it depends upon the surroundings, whether the solids at the rest or the solid structure is moving with the velocity v. With a no slip conditions, all the fluid particles here also moving with the velocity v. If you have two fluids, their interactions also play the major roles. So that way you try to understand it how the interactions happen with the neighbors. Okay, that's the fluid properties, and that is the reasons we uh, brought it your concept of velocity uh, field, the pressure fields, and many of the times we told it that shear stress field. Okay, anyway, in this course I have not gone to that level. No. All these what it makes a confusions in the fluid mechanics, which is cause, which is effect, because all are interacting each others. So that's the reasons you try to understand the fluid mechanics as a application standards and as if visualizing the flow process. How the Navier-Stokes equations okay can be applied for real life problems. As I said it, there are a lot of problems now we have been solving with the use of the Navier-Stokes equations. Uh, Almost these climate models, the flow models, what you talk about the river flow, you talk about the climate models, we predict the weathers. Nowadays we are predicting the weather very accurately, so within a half an hour intervals. We are predicting the cyclone tracks, okay, within a half an hour interval accuracy. So how it is possible? Because of our fluid mechanics knowledge. And the basic equation is the Navier-Stokes equation. The many studies has been done it how to get the solutions of Navier-Stokes equation, which is the computational fluid dynamics or some analytical solutions are there. So that's what is give us, as I said it earlier, you want to have this computers, animations, navigations, feel a virtual, okay, like you do a car drivings or in gaming, okay. What you have to very close to that conditions. That's what will be, you will get it when you back end you there is a solutions of Navier-Stokes equations. So that's the things. That's the reasons you feel as close as the natural conditions. As that's what is the virtual reality. So that there are a lot of applications are there, but that's what I'm to tell it. Okay, I think this part we have already said is plotting object. Some more objects you can think about. Okay, beneath the subclass. Okay, you just think with respect to the plotting objects. Okay, I think again we have put it the graphs, uh, figures. I think it's a very nice figures, and if you swim it, that's what you try to do it, the balancing it. A swimmer is always try to do the balancing. Okay, so if you look at the buoyant force and the CG, try to balance it. That's the reason you just think it what the swimmers does it. Okay, Minal Burma, Navier-Stokes theorem. Okay, I think the basic idea I'll say that I can always discuss about Navier-Stokes equations, but these codes we are not limiting beyond these Navier-Stokes equations because we try to look at it's an undergraduate course, it's the first level of the fluid mechanics course. First have a confidence on this, then you can go for the second level course where we talk about Navier-Stokes equations. There are many NPTEL courses are there, but this course is designed to give the understanding still the Navier-Stokes equations with some numerical examples, the experimental uh, lab conditions. We try to give it a level 1 the fluid mechanics. So that's the reasons. Please try to ask the questions which is related to this uh, regarding fluid properties. I think because we are not getting the idea what is you are looking at. What is you are looking in fluid properties? Okay, either you are looking for density or you are looking at what is you are looking the surface tensions. What is you are looking at? So please clearly write the your queries. We'll try to explain you. Okay. Okay, again the similar type of questions for Konal. Physical properties of fluid mechanics. Physical properties of fluid. Okay, so you know about that densities, specific gravities, the surface tension, the capillarities. For the liquids, okay, for gases also we can have the properties. Okay, that what very basics we have covered it. Can you provide a sessions on open channel flow? Okay, Nirmal Kavyasri. Again, I'll tell it. This course is for fluid mechanics. It's not for open channel flow. We don't have our syllabus to teach the open channel flow, but we are looking at. Okay, so similar things will come up. May not for the you. Maybe in near futures we'll have a extending this fluid mechanics course to next levels. Others, Sahebaru Duba. Okay, is the depth with which a particular discharge attains only depends upon hydraulic radius of channel, or else there is any other concept? I think this questions is related to river engineering. I also have another course is the river engineering. There I'll explaining you with respect to the specific discharge curves. Okay. Now I think this is fluid mechanics part, so I'm not answering it, but please attend my fluid. Okay, so there is a general questions as you expected is that how to prepare the GATE exams. Okay, again I need to repeat it and to tell it. Please have a conceptual understanding of the fluid mechanics. That's the reasons again we are many of the times we have seen the best classical books. Okay, on the fluid mechanics like F.M. White, Sinjal Simbala, or the same series, where there are the problems are there which is even if you solve the 10 problems, but 10 problems are the 10 different types, and you also have a trend how to use this control volume, how to use the stream tube. So if you try to uh, looking for to qualifying these GATE exams, please establish the conceptual knowledge on the fluid mechanics and do some numerical examples. The solve some numerical examples. We tried our level best to teach on blackboard and giving some examples from GATE exams, even if your some of the assignments are coming from GATE exams. So if you look at that way, we are giving the questions level which is coming at the GATE levels, but as I again and to repeat it, any GATE exams they never repeats it the same questions. Always the questions are the different. So you please try to have a conceptual understanding and problem solving skills. If you do that, I think that's not a big issue whether you want to crack GATE exam or not.
Okay.
Okay.
Some of questions.
Hmm.
So first question: when we measure capillarity height from Abhinandan Sagar.
Okay. Yes.
When we measure capillarity height.
When
We measure capillarity height, then after that nothing is there.
Abhinand Sagar, your question is not that clear cut. Okay, what is you are looking at? Okay, how do you measure the capillarity height? So that's not a very clear cut for us. But you post the questions in Google Forms. We will try to explain.
The next question asked by Vipul Bandwara sir. Why water always follow the wet path then dry one? From wet path to dry one.
Before Bathware, see, water always flow it. Don't be confused yourself. Any flow process which is happening, it is always having the flow from higher energies to the lower energy level. It looks from the higher energy to lower energy. Okay, it travels from the higher energy to lower energy. Whenever it travels, it also dissipates the energy. Whether it has to follow the wet path or dry path, you look it in terms of energy concept, the availability of energy, and which is the path which has to follow it. So please don't be look it very segregatedly, whether a wet path or dry path. You look at the energy point of view, as we have done energy gradient line, the hydraulic gradient line. Those concepts you try to understand it. Okay, so don't look at the dry path or wet path. Okay, uh, so try to understand from the flow happens from the higher energy to the lower energy. Okay, and whenever the flow it, some part of the energy dissipations happens it. Okay, so whether the flow is fast or the low, all that is the reasons we have the equations for that. You need to try to know it how much pressure drops happens, what is the velocity increase is there, what is the potential energy difference. All you look at this minutely, each component of bundles equations. Okay, and you can try to understand it when you are looking.
So next question is from Abhinav Chaudhary sir.
Mm.
Is it possible for an airfoil partially submerged in water to generate lift?
Okay, Arvind Chaudhary, is it possible for airfoil to partly submerge in waters?
To generate lift.
See, that's when if I look at your problems, if I understand properly, is that you want to make a airfoils which will have these two fluids. One is water, one is the air. It it is depends upon the lifting forces happen because of the pressure difference. Lifting process happen due to the pressure difference. As you have the two fluids, you try to understand it that whether that much of pressure difference we can generate it at the interfaces of these ones, at what velocity we can generate it. That's what is not a very straightforward answer for you. But if you look at what is the problems you have either aerofoils or your flight. Okay, your flight is moving with the velocity v, which is a partly submerged in water, partly floating it. Whether it will be the drag force, lift force will be there or not. The lift force is depends upon the pressure diagrams. Okay, so that is the reasons you have to need a more studies, and you try to look at this problem in that way. There is a no shortcut answer, the yes or no for these cases.
So next question from Abhinav Chaudhary only sir.
Uh,
The velocity profile of laminar flow in a square pipe.
Oh, okay, I think we have not come to the pipe flow, and so velocity profiles how it happens. I will say that uh, pipe in a circulars we know this is a parabolic, okay, distributions for laminar flow, but if you try to understand it, you will not have this similar natures when you have the square pipes. But what is the distributions? Those anyway we have not come to the pipe flow levels. When it would come, it depending for we will show to you. That's not a big issue. But you try to understand it, the pipe flow, what we have a parabolic distributions in case of laminar flow, that doesn't happen it when you have the square pipes, because you try to understand how the vortex formations happens it. You try to understand it. Okay. So if you look at this, if you have a corners, definitely there is a vortex. The secondary vortices are going to form it. So based on that, you try to understand it. What would be the velocity distributions in a square pipe? Next.
So next question from Abhinav Chaudhary.
Mm.
How to calculate fluid velocity and streamlines near particle with COMSOL?
Okay, I'm not using the consoles. Okay, I don't have to look at how to calculate the fluid velocity streamline.
And streamlines near particle.
I'm not using this consoles. Okay, I have not gone through these consoles. What it does it. Okay, so I think this questions is not much relevant to us. But okay.
Sir, in CFD course, it is asked by Mohan sir. Actually, I have enrolled for CFD course and I asked there one question. Why don't we use ideal gas equation for air medium for incompressible flow Mach number less than 0.33 as a equation of state for close the system of equation. But they said in discussion forum that we cannot use the ideal equation as the equation of state and it will give erroneous results. So he is asking why cannot ideal equation for Mach number less than 3.3.
I'm not getting that way. This B1, I'm not getting that way questions. Okay, you might have asked some questions to the CFD course instructors. Okay, but what I try to look at is that if I tell is flow is incompressible. Okay, and I try to look at how much of density variations happens. Try to understand that. Okay. Don't look at because as a engineers we don't look at density doesn't vary. It is a constant. It doesn't happen. It there will be a because of the pressure difference, because of basically I'm talking about air. There will be some degree of change, some change in the density. But is that density is a significant for that particular flow field? If it's a significant, then you have to consider the density variations. For in terms of energy dissipation, in terms of vorticity generations, the flow patterns. So if you look at that way, always you look at what type of problems you are solving it. But most of the times it is found it that when you have a Mach number is less than 0.3, in that periods the flow behaves like a incompressible flow. But if you have the shock formations and all, so we cannot have that. Okay, so that's the reason. So you need to know it that where the density variations are affecting the flow, other characteristic like velocity and the pressure field, how much. But overall guidelines is that when you have a Mach number less than 0.3, the density variation can be considered as negligible to affecting the velocity field, the pressure field, and energy dissipations. So those things you have to look at that how it happens it. But some particular cases you can have a different conditions.
So next question asked by Manoj sir.
Okay.
Difference between steady and unsteady flow.
Okay. So if there is Manu, the question is that what is the difference between steady and unsteady? If you look at most of the flow is the unsteady flow. Okay. So basically the pipe flow, the flow as an object, you you are doing any flow processes happening in our biological body systems all are unsteady. But many of the times, what do we try to look at that uh, make it a steady problems, because many of the times like a pipe flow, if I am to design a pipe systems, I just look at very high flow conditions, what is the pressure develops, whether that pressure can be pipe can resist it. So that way we don't bother about, don't look at more depth during the transient periods. So we simplify the problems from unsteady to steady. Same way, if you look at some of the good books, how they use this frame of reference, they change it and they make it the unsteady to steady problems. So the steady, when you do it, you look at that, you simplify your governing equations. As you simplify the governing equations, your solving the techniques are quite easy because you drop the time components. So that way you try to understand it. But if you are try to look it in terms of the velocity field, if I very simple way, which is there in many of the textbook, unsteady flow, there will be time components in a velocity, scalar components, the pressure field. But in steady flow, that is not there. But please look at not that way the definitions. We try to look at how we can simplify it, because almost all the flows are the unsteady flow. Unless otherwise very regulated flow where you will have a steady flow. But we try to design a systems for the extreme conditions, extreme flow conditions, extreme pressure conditions. So we look at that extreme behavior. That's the reasons we drop the time dependent components, make it the problems in the steady natures. So I have given in two examples. One is basic from your fluid mechanics books, which they define this velocity is a function of space and time. For the unsteady flow, for steady flow, they have just defined with a space. But in the real life problems, how we really simplify this unsteady problem to steady problems, because that's easier for us to solve the problems.
So next question asked by Abhinandan Sagar sir. Why we consider more on rolling than pitching while constructing the ship?
Abhinandan Sagar, we are not going to that details, okay, rolling and pitchings and this part. We are just talking here very undergraduate level things, but if you are really looking about those things you can look at, okay, and you know the basic concepts of rolling and pitchings, how does it happen, that part we can look at. Okay.
Next question from Pushpendra Singh, Singh sir. Average velocity variation before fully developed flow in laminar case, is it constant or not?
Okay, Pushpender Singh, I think you just wait for the pipe flow to commit where we commit, okay, because I don't want to make it everything across from space to these things to give the answers. But what I'm looking at that you try to understand what type of flow patterns are happening, how the velocity variations happens. Okay, so if you try to understand that how the secondary flows are happening, then you can get the solutions for that. I think so we have taken a lot of time.
Yes.
Okay, so almost 50 minutes. So we don't have more questions. I think with this, let me conclude these interactions. Thank you, Dot, for attending this.